So it could be worse, right, guys? Ladies?
Yep.
Okay, so here's the plan. We're going to review the past 3 homeworks. Then we're going to go over the error PowerPoint, which is not super long. Then, that'll be it. So, won't be a super long class today. Reminder that homework 8 about the chi-square is due next Monday. The discussion board, which is about errors, you just have to find an article that is a meta-analysis, and then summarize it. And you have to respond to one other person in the class's post, and you get extra credit if you respond to more than one person. It's all in the prompt listed there. And then we do not have class next Monday because it's Thanksgiving and everyone needs a break. But if you want to meet with me, I will be available. You just need to let me know by Friday so that I plan to stay here on Monday. Otherwise, I will not be here either. Or Tuesday. I can meet Tuesday evening too. There's some other reminders over there about my office hours and that meeting next week. And I won't have my Thursday evening office hours next week because it actually is Thanksgiving. So, any questions about that? Okay. So first we'll go over homework 5. There's 2 that I want to go over, and then if there's any other ones that everyone or anyone is concerned about, we can talk about them. So the first one that a lot of people did incorrectly was 1C. So we wanted to find the percentage of the population that fell between 2 scores. So we had to find 2 z-scores. A lot of you did this part correctly, but then instead of subtracting one from the other, which since one of them is negative, you would have to add them together, you found the z-score in the table, their proportion in the table, and then you added those together, which gives you a different result because you use a different column if you're doing it that way. So first we'll find the z-scores, so the mean minus the population mean divided by the standard deviation for the lower score and then for the higher score. Then we subtract the higher one or the lower one from the higher one, and since this lower one is negative, they get added together, so our z-score at the end of it all is 2.438. Now if we look at the z-table, let me flip this a little bigger here. This last this last column here has a range of values from below the mean to above the mean. So it's not using this to find this first column, and then using the same column to find the other one and adding them together. You had to add the z-scores you calculated together and then use this column. So we find, what did I say it was? 2.438. In this table, it's all the way down here. 438. So it'll be 2.44. And then we go all the way over to this last column, and it's 0.9853. So to turn that into a percent, you multiply by 100. So 98.53% of the population has the IQ score between 80 and 119. Which, if you think about it, makes sense. Most people don't have, they either have a low average or up to elevated IQ. You're not going to have a huge part of the population who's highly advanced or gifted or superior, and you're not going to have a huge part of the population who's moderately impaired or mildly impaired. So that's that one. Then the other part is just in reference to kind of the rest of them. When you find the CV range, the critical value range, so for this example, we'll do number 3. So here it's plus or minus 1.96. Then when you calculate your z-score, you want to see if that value you calculated falls in between those two values. So that's why I like to draw out this number line so I can visually see where everything falls. So the z-score we calculated is negative 4.97. The lower limit of the CV region is negative 1.96. The mean is 0. And the upper range limit is 1.96. So since negative 4.97 falls outside of that range, that means that, what does it mean? That it's statistically different. So since this doesn't fall in our expected range, this critical value, it is statistically different. Now in this last example, the value does fall in the range, which means our sample mean and the population mean are not statistically different. Does that make sense? Okay. Any questions about this homework? Other than those couple I just talked about. Okay. So that's graded and posted, and I left feedback too, so if you got something wrong, I explained it. On to homework 6. So for the most part, I'm going to say that everyone got part 2 either correct or mostly correct. So good job. People got messed up on these multiple choice questions. So the ones I want to go over, I mean, we can go over all of them, but the first one, okay, so the first one is a little difficult. So since the majority of people overall in the 2 classes didn't get this correct, I'm going to give everyone a point for that. So your grade will be updated eventually. But this was supposed to be D, that z-score evaluates individual scores, while the t-statistic evaluates sample means. Okay. Number 2, for the most part, everyone got 3. 4, again, you have to use that formula, so 27 minus 15 divided by the standard deviation, which is 1.5, should have given you 8.00, which is B. Number 5. So, a lot of people did not get this one correct. So we have to remember that the degrees of freedom formula is n, the sample size, minus 1. So if we look at the degrees of freedom, we can determine how big the sample size is. Because if the sample size is 1 plus the degrees of freedom. So if we have one of those pieces of information, we can determine the other. You can't determine the research hypothesis by looking at the sample size. You can't determine the null hypothesis just by knowing how many people are in your sample. And you can't determine the alternative hypothesis by knowing how many people are in your sample. So that's number 5. Does that make sense to everyone? Okay. Number 6, if the value of a t-statistic falls between the critical values for alpha of 0.05 and alpha of 0.01, you would describe the level of significance as p is less than 0.05. So if you think of a value between 0.05 and 0.01, it could be 0.03. Let's say that. That's less than 0.05, but it's not less than 0.01. So it can't be C. And if it's between 0.05 and 0.01, it's not greater than both of them. It's definitely not greater than 0.05. But if it falls less than 0.05, it can't be considered greater than 0.01 because we try to report less than as much as possible. Does that make sense? Number 7, so this one, you're basing your sample on 13 participants. You calculate a value of 2.26. For the t-test, your alpha level is 0.05. So how would you interpret that? Well, if the alpha is 0.05, we're not going to be reporting at the 0.01 level. So automatically, these 3 are out. Then this value in parentheses here is the degrees of freedom. So to calculate that, you'd use the sample size 13 minus 1. So it has to be B. Does that make sense? Okay. Everyone in this class got number 8 right. Good job. Number 9. What is the term for the lower and upper boundaries of a confidence interval? These are the limits, the lower limit and the upper limit. So it is a confidence interval, but that's not what those individual points are referred to, and the point estimate is not the limits of it's not that upper and lower point, it's the middle point that we're looking at is the point estimate. And there's no such thing as an interval estimate, so. Number 10 is B, the mean. So when we write up our summary, we say we're 95% sure that the confidence interval contains the mean of whatever. So that's the mean. Number 11, what is the relationship between the size of a sample and the width of a confidence interval? So I guess to best explain this one, you want to think about that confidence interval formula, which is the point estimate, or your mean, plus or minus that margin of error formula, which is z times something divided by the mean, the square root of the sample size. It's z times the standard deviation divided by the square root of the sample size. Sorry. So since the sample size is included in that formula, the size of the sample will influence the range of the interval. So there is a relationship, so it's definitely not D. But it's in the denominator of the formula, so as the sample size increases, that means there's an inverse relationship. The confidence interval will decrease if sample size increases. So decreasing meaning getting smaller, becoming more narrow of a range instead of getting wider. And the next few of these kind of ask the same sort of question. So a sample size of which of the following would have the narrowest confidence interval. So the higher the sample size, the narrower the confidence interval. The more people there are, the more certain we are that we have the true mean estimate in our range. So the number 12 is D. Number 13, the blank the sample, the more confidence we have that the sample estimate of the unknown population mean, and the blank, the confidence interval around the sample mean. So the higher the sample mean, the smaller the confidence interval. Number 14 got a lot of people messed up, and so I'm going to draw a picture because that makes it easier. So let's say our mean is 115, and we have this range of values. I know it's not a straight line, I can't draw straight. So we have one confidence interval that's 112.5 to 117.5, and so that's one confidence interval. And another one would be 112 to 118. And then the last one, these are not the right distance apart. Sorry. Is 111 and 119. So this first one, 112 to 112.5 to 117.5, this is a 90% confidence interval. We're 90% certain that the mean of the population falls in this range. The second one is a 95% confidence interval. We're 95% sure, we're more sure that it falls between a greater number of values. Does that make sense? And then the last one would be a 99% confidence interval. because we're 99% sure it falls between 111 and 119. But it gives us more room to be wrong because we're more, so the larger the confidence interval, the more room we have to be wrong. I mean, no, that doesn't make sense. The smaller the confidence interval, the more room we have to be wrong. Because the smaller this is, there's a greater chance that what we find in the true population is different than this. But when it's bigger, there's a greater chance that it's going to fall in between that range. So if, let's say, the true mean for whatever we're looking at is 110. Well, that means there was a 1% chance that it could be outside of this biggest range we had. If the real mean was 112 point, wait, this should be 113. No, hold on. Yeah, no, that's right. 112. 111.5, that falls in the 99% confidence interval, but not the 95% confidence interval. So the answer for number 14 is D. So it's the most precise because we're the least confident that our true population mean will fall in that range we specified. Gotta turn the TV back on, sorry. And then the last one's number 15. So if we reject the null hypothesis, that means that the result is significant. So if you think back to that range of the confidence interval or the critical value region, if our estimate falls outside of that region, then we reject the null hypothesis. So we find a significant difference. If our answer falls inside that region, we accept the null hypothesis and find that there is no significant difference between our mean and the population mean, or R value and the sample's value. So immediately you should have narrowed this down to significant or non-significant, because insignificant is never going to be spoken in statistics. There's either significance or there's not. There's not an insignificant amount of something, and there's not a highly significant amount. It's one or the other. Any questions about homework 6? So remember that the lowest grade for the semester is dropped, and then your highest score for homework is doubled. So if you didn't do as well as you'd like, it might be your lowest score, and then it'll be dropped. And there are extra credit on some of the other assignments. So if you did above the score for other assignments, those will get added to your final score. I redid the grades in the grade book. I don't know if you guys noticed. One of the people in the other class, the online class, emailed me and was like, my grades are different. One book said the D2L assignment says something, and then the grade book says something else. So I fixed that. So they should say the same thing now. And for assignments that you scored above the max point value, those points will now show up. So if you scored below the max point for another one, it'll even all out in the end. Happiness, gladness, excellent. Okay. All right, now we'll talk about homework number 7. Yay! So this was due today. So the first two, part 1, number 1, A and B, you just had to identify the independent variable, dependent variable, and which test that should be used. So number 1A, the dependent variable was heart rate, measured continuously. The independent variable was gender, measured nominally as male and female. And because these are independent categories in the IV and we have a continuous DV, it is an independent t-test. And remember, this homework, we had only covered independent t-tests at this point and paired t-tests, so those are your only two options. So if you put something else, oops, then number B, whatever. The dependent variable is anxiety measured continuously on this out of 15 score, and the IV was lecture type, measured nominally as a normal class versus a disruptive class. And then the statistical test is a paired t-test because these are the two class types. Does that make sense? Okay. Then number 2. So we went over how to put this into SPSS in class last week. So I'm not going to do that again. If you were not here, it's in the lecture posted last Monday or Tuesday on D12. But the DV and IV, DV was post-treatment cholesterol concentration measured continuously. IV was treatment measured nominally as diet group or exercise group. And since it was a continuous DV and there were independent categories, it's an independent t-test. Yay! This is what your data should have looked like in SPSS. If you don't have the ID variable, that's okay, but I like to have it so I don't forget things. It's a habit. And then your results, when you write it up, it should look similar to this. So equal variance is assumed. An independent t-test found the mean post-treatment cholesterol level was statistically different between the diet group, that's their mean and standard deviation, versus the exercise group, their mean and standard deviation. Then the statistics, T degrees of freedom 18 is equal to negative 3.803 with a p-value of 0.001. You can either write it that way or p less than 0.05, since 0.001 is less than 0.05. It doesn't have to say exactly that as long as it contains all the right numbers and stuff. That's what I'm looking for. Number 3, we also went over how to enter this into SPSS. The DV was number of poor health days measured continuously. The IV was assessment time measured nominally, 2010 and 2015. So since they were the same group of people measured 2 time points, it's a paired t-test. I know you can't see this data, but this is how you would enter it. The first column is my ID column, and then the 2010 is in this left column, and 2015 is in the right column. And then the write-up for this is a paired t-test found the mean number of poor health days in Seattle was not statistically different from 2010, mean standard deviation, 2015, mean standard deviation, T, degrees of freedom 24, T value is 1.133, the p-value is 0.269, or p is greater than or equal to 0.05. Last one, yeah. Number 4A, how many tests were computed in this pre-filled out table? 3, because there's 3 p-values. If there's a p-value, at least one statistical test was run. What are the independent and dependent variables? The dependent variables are these pre-surgery characteristics, age, weight, BMI, and they're all measured continuously. And the IV is post-surgery condition at the 12-month follow-up date, and that's measured nominally as either they were a success or they were a failure, based on this excess weight loss formula. And then to describe the characteristics which were statistically different between those who were successful and those who were not, I used this little write-up here. So as compared to those people who were deemed a failure, those who were found to be a success displayed a statistically lower mean pre-surgery BMI. That's because this p-value is less than 0.05. Weight and age are not statistically different in this sample because p-values are greater than 0.05. Questions on this? Everyone pretty confident with their homework submission? Maybe? Yeah, okay. So I'll post the answer key then so that you have it. Actually, I'll do it now, that way I don't forget. It'll be posted in Module 7. Oops. Okay. There you go. Now it's there. You have it for all of posterity. Before we go in the lecture, see, I told you it was going to be short today. I just want to go over the discussion board. So it's just talking about effect size, which we'll talk about a little in the lecture. You have to find an article, so you can use the library's website, Google, whatever you want. It needs to be a meta-analysis. So I gave you some tips for how to find one of those. If you go onto the library's website from here, one of your search terms can be meta-analysis, and then in the title it should always say meta-analysis. So if it doesn't, probably not a meta-analysis. Just, if it says it in the title, it definitely is. So go with that. It can be on any health-related topic you're interested in. I don't care. There's tons of them out there on every topic you could imagine. You just need to write up what the article you're looking at found in a few sentences. Okay, a paragraph. And then you're going to respond to someone else's in the class with a couple sentences. It doesn't need to be anything crazy, just, oh, this is very interesting and I know XYZ about that topic. Or I did something similar in my whatever class and we talked about this too, cool. Or, wow, this is really surprising, I didn't know that this happened. Something like that, okay? And then if you would like extra credit, you can respond to an additional 5 other people's posts and you'll get 5 points if you do 5. If you do 3, you'll get 3 points. As long as you do this one, you'll get full credit for this discussion board. If you do more than that, you will get 5 extra points at the max. Fair? Pretty fair. That way if you don't want to do extra, you don't have to. Okay. Oh, and make sure you put the APA citation for your article so that if I'm really interested in it, I can go find it. Thanks. And if you don't know how to do APA, you can always post it and then ask people to help. And that could be your response, is helping them figure out how to use APA format. Okay. Now we're going to talk about this fun and exciting stuff here. So I know some of this will be a review, but I had the lecture put together and posted before I looked at it, so sorry. If you're confused with dependent and independent variables, here is a little description. So dependent variables, the value is dependent on the effect of other variables, or it's the event or outcome who we're looking to see the variation based on the independent variables. The IV is the characteristic being observed or measured, and it's what we think is going to influence that dependent variable or the outcome. Or it could contribute to the variation. That would be another test we haven't gotten to yet. Here are some examples. A scientist studies the impact of a drug on cancer. What is the independent variable? Anyone? The administration of the drug, so either they did get it or they didn't. And the dependent variable would be their cancer status. So did they improve or not improve? That was a pretty tiny little question to get all that information. This is a better one. So there will be a statistically significant difference in graduation rates of at-risk high school seniors who participate in an intensive study program as opposed to at-risk high school seniors who do not participate in the program? What's the independent and dependent variables? So let's do the independent variable first.
Study program?
Mm-hmm. So did they participate or not? Yes or no? So that would be measured how? Nominal, ordinal, or continuous?
Nominal.
Nominal, yeah. And the dependent variable is graduation status. Did they graduate or not? That's also measured nominally. So what test would we use if we were going to run an analysis on this? Chi-square, yeah! Woohoo! I'm too excited, I know, it's fine. A director of residential living on a large university campus is concerned about the large turnover rate. Okay, this is really long. I'm just going to let you read it. So here, what's the independent variable or variables? Any ideas on the independent variable?
Attitude.
So knowledge of the position is one, attitude towards the policies is another, and then the third is the ability to handle conflicts. So there's three. We haven't learned this test yet, don't worry. We'll get there, but not yet. And then the dependent variable is the commitment to the position. So are they going to continue for 2 years or are they going to not continue for 2 years? Does that make sense? Cool. Significance. So here's written out kind of some of the things we've been talking about. So in order for something to be statistically significant, the observed value must be too large to be explained by chance. So it didn't just occur by chance. There's something real that's different between one group versus the other group, or whatever your independent variable is. So again, the significant level in this class will be alpha of 0.05, which means that we look to see if the p-value is less than that. It's kind of an arbitrary value that someone picked because they liked it. And there's a whole ton of, if you're interested in debating that, you can look online because there's a ton of debate information about it. Just because a result is statistically significantly different does not mean that it's clinically significant. So just because your sample has a different statistical difference between their cholesterol levels in your program group and the non-program group, maybe that's like a 0.5 milligram per deciliter difference. Is that really that different in clinical terms? Not really. So even though you found a difference in your statistics, in terms of clinical practice, it doesn't make a difference which program they do. Does that make sense? I know that gets confusing, but you can measure clinical significance in a number of ways using effect size or the number needed to treat. We're not going to talk about number needed to treat. That's more epi. So if you haven't already learned about that, you will, or you should. If you don't, you should look it up because it's on all of the exams that you'll ever have to take in order to get the CHES or CP license thing, if you're doing that. If not, don't worry about it. P-value, so this is the probability that the difference or relationship has occurred by chance. So the smaller the value, the more likely there's a real difference, that it's not just, or that there's a relationship between the variables. And again, SPSS provides the exact value. I said you should report it to 3 decimal places, but you don't have to. Either 3 decimal places or the less than or greater than or equal to 0.05. Either one's fine. Effect size. So this measures the strength of relationship of variables. It's the magnitude of the difference between groups. There's two different ones that we're going to talk about, but there's tons of other ones that are used. So if your article has ones that we didn't talk about, that's fine, because they'll still mention that it's effect size. So first we'll talk about Cohen's d. So this is the difference between two means divided by the standardized mean difference. What the heck does that mean? Basically, this effect size allows you to compare two studies that are on a similar topic, but maybe didn't use the exact same measurement. So maybe your study measured heart rate and my study measured blood pressure, but we are both looking to see effects of the same program on diabetes. We can calculate this effect size to see if the effect of my program was the same or better or worse than the effect of your program, even though we didn't both measure heart rate or we both didn't measure blood pressure. It's calculated as a lowercase d, and you interpret it on the scale that's here. So 0.02 or 0.2 is a small relationship, 0.5 is medium, and 0.8 is large. So this is on a scale of 0 to 1. So the closer you are to 1, the larger the effect of the program that happened. So what we would do if we were comparing my program to your program is I would calculate the effect size for my program. You would calculate the effect size for your program. And they would both be on the scale of 0 to 1. And maybe yours comes out to be 0.8 and mine comes out to be 0.6. So your program was more effective than my program was. Does that make sense? Pretty cool. This also talks about the mean difference in two dependent variables between the exercise and control group. So you would calculate it for each study and then compare the studies, which is what a meta-analysis does. So it compares a number of studies on a similar topic to see which is most effective. And that is more helpful than reading individual articles about a program, because it helps you know what has been most effective by reading one article instead of 100. And then once you find which one's most effective, you go and read that article. So you read 2 instead of 100. Isn't that exciting? Yeah. The other one that we're going to talk about is the partial eta squared. So it's this weird n, which is called an eta, and it's squared. That's what that's how you would write out what it is, or that's what you would see in an article. This measures the proportion of dependent variability that is attributed to a specific IV and the mean difference in the DV between the IV groups. So for example, if mean BMI was found to be statistically different between an exercise and some other group, maybe they just get a pamphlet, we found that that is less than 0.05, our p-value. So then we compute this effect size to determine clinical significance. Now we're not going to actually calculate these in here because it's really complicated and SPSS does not do it for you, so you're off the hook. You just have to know about it. The partial eta squared would be equal to 0.75 for the main effect program. That's considered a large effect. So this is for the group that exercised. And a partial eta squared of 0.15 would be considered a small effect. And maybe that's for the control group. That's what they got. So there was no effect in them, or there was a small effect, and in our program group, they had a bigger effect. So there was a bigger change. Does that make sense? Kind of. Okay. Oh, fun. Now we're going to talk about decision-making errors. So When we use hypothesis testing, which is the null hypothesis and the alternative hypothesis, we're using probability. We don't talk a lot about probability in here because then people get upset already. You're already upset because you don't want to do SPSS, and then you put probability on top of it, and like the world collapses. So I skipped over it for you. You're welcome. Because the decision is based on probability and we're not certain 100% of what we're finding, we can always make a mistake. Now, this is not like a math error mistake. This is like something went wrong when we collected the sample, so it's not truly reflecting what's in the population. Things like that. It's not like I added 1 instead of 100. So it's not that. There's 2 types of error. Type 1 is when you find that there is a difference between 2 groups, when in the real population, there is no difference between the 2 groups. And this is referred to as the alpha level. So this is why we set it at a specific level, because we want that 5% chance we want it to only be a 5% chance. We don't want it to be more than that. The probability of not making a type 1 error would be 1 minus the alpha, or 0.95. That would be a 95% chance of not making a type 1 error. So why could this be a concern? Why is saying that there is an effect of your drug treatment when it doesn't actually have any effect? Why is that? Why would that be bad? So if you're testing a drug for anxiety and you're saying that your drug helps reduce anxiety, but in real life it doesn't, there's no difference between the people who take your drug and the people who don't. What does that mean?
Making a false claim.
You're making a false claim, exactly. What you're saying to the public is, here, take this drug, it'll help you reduce your anxiety, and it doesn't do anything. So that's bad. We don't want this to happen. So why does it occur? Usually it's just due to chance, because there's always a chance of things happening, and fluctuations in sampling. So maybe you collected someone in your sample, you collected them. Maybe someone in your sample was super high anxiety level, and that threw all of your results off, because when they took this drug, it made them feel better, like a placebo effect, even though it didn't do anything in everyone else. So, who knows? That's type 1. Type 2 is concluding that there is a difference, that a difference is not existing between your 2 groups when there actually is a difference between them. So this is saying that you gave everyone this drug and the drug didn't help them, but in true life, the drug did help them. This is known as beta. It's difficult to determine that, so often we calculate 1 minus beta, which is known as power, and this is the ability to detect when an effect does exist. So why could this be a concern? You may not communicate your results if you didn't find anything in your sample. So maybe this drug cures cancer, but you didn't find it in your sample. But you don't publish because you didn't find anything. So now no one else knows about this drug. That'd be terrible. This happens because of chance or research design issues. So using a convenient sample, like standing outside this building to get survey information instead of going across campus to multiple locations to collect data. So it would be based on how the data was collected. So here's some more examples of type 1 error in medical testing. It would be a false positive. So the person doesn't have the disease, but the test says they do. Or convicting an innocent person, or concluding that 12 hours of class in one day causes burnout when it does not. That would be an example of type 1 error. And then type 2 error, a false negative. So the person has the disease, but the test doesn't say that the person does. So this becomes a problem in HIV testing. If your test tells you you are not positive for HIV, but you really are, you may not use those protective behaviors, and then you may be transmitting HIV to other people. This in court, it would be not convicting someone who's actually guilty, and it would be concluding that 12 hours of class does not cause burnout when in fact it does. Those examples help. And here's another way to look at it. So if you think about those 2x2 tables for chi-squares, or the odds ratio and risk ratio we did at the beginning of the year. So if in the true population, there's this test to determine if you have diabetes or not. And you have a new test you're developing and you're using this old test as well. So you have the same group of people, and your test either says that they have diabetes or not, and the standard test is saying whether they have diabetes or not. So if your test says they have diabetes and the standard test says they have it, that's the correct conclusion. That's what we want. If your test says that they have diabetes, but they don't actually, based on the standard diabetes test, that would be a type 2 error. If your test says they do not have diabetes, but in fact they do, based on the standard test, that's a type 1 error. And if they do not have diabetes based on your test, and they do not have diabetes in the standard test, that's the correct conclusion. So these two are the ones we want. We want them to match. We don't want there to be an error. So again, power is 1 minus the beta, which would be type 2 error. So you can actually calculate power and determine how big of a sample you need in order to have enough power to reduce the type 2 error. And I think I talk about that in one slide from now. Some ways to control type 1 and 2 error are on here. So controlling a type 1 error makes it more difficult to reject the null hypothesis. So we could lower the value of alpha from 0.05 to 0.01, but this also increases the chance of making a type 2 error. So the more difficult we make it to reject the null hypothesis, the more likely we are to miss that there really is an effect of the drug we're using. There's a lot of ways to control type 2 error, so a lot of times this is what's focused on. So it makes it more reasonable to reject the null hypothesis. So you can increase your sample size. You can raise the alpha level, but then you increase the risk of having a type 1 error. So we don't really want to do that. But we can increase the sample size. That's usually pretty easy. We can use a directional alternative hypothesis. So instead of using that two-tailed, we think there is some difference between our population and, or our sample and the population. We could say, we think our sample is greater than the population, and then we only have to use one side of the normal curve. We can increase between group variability or decrease within group variability. We're not getting into that too much because that's too much, but these are some ways that you can control it. So if you ever have to, in research methods, potentially write about how you would do that, here are some ways you can. Statistical power. So there's a lot of arrows here, but let me talk it out. So statistical power is influenced by sample size, significance level, the variation in your outcomes, and the difference or the effect size that you're detecting. So the relationship between sample size and power is a direct relationship. So as the sample size increases, the power increases. Same with significance level. As your significance level increases, the power increases. The variation in the outcome, so that's kind of like the standard deviation. As that decreases, the power increases. So the lower that space between the lower limit and the upper limit, you can think of it that way. The lower that is, or the smaller or narrower that is, the more power your result has. And then the effect size. So as the effect size increases, so as that number gets closer to 1, your power increases. Does that make sense? It's great. Super exciting, I know. There's a couple ways to do power analysis. We're not actually going to do it, but I want to show you what it looks like. So if you're going to do a post hoc power analysis, this would be you already did all of your analysis, and now you want to see what the power of your analysis was. This is not ideal, but it happens a lot. So you're answering the question with this power analysis of, did I have enough power to actually detect a difference, if it really existed? So here is what it looks like on this G-Power. G-Power is a free app to use for power analysis, but you enter in a whole bunch of things, including in this determine area, you put in the number of people in the mean and the SD of your two groups you're comparing, and then you can calculate that effect size, the D, Cohen's D we were talking about. So this is an effect size of 0.448, which means it's a moderate effect size. And then you also put in your alpha level of 0.05 and the sample size of your groups. And then once you do that, you click calculate, and it shows you the differences in your two groups and gives you all this other fun information. So your power is this value here, 0.72493335. This is the ideal way to do a power analysis, the a priori. So you do this before you collect your data and analyze it. It helps you determine what your sample size should be to see a difference in your independent variable groups. So we use a lot of times data from other studies that have been done to kind of guess or estimate what we should, the group size to calculate the proposed effect size. So again, using the G-Power app, comes up with this screen. We're looking at t-tests here because we already talked about them, but there's other things you can do with this. It just gets more complicated. So there's this button here for do the a priori. The other one was post hoc. And then here you'll put in the effect size. So we're using the same effect size we calculated in that other one. So we want our effect size to be that, at least that, 0.44. Our alpha level is 0.05. Power, we want our power to be 80%, which is high, which is the standard. You want your power to end up being at least 80%, ideally. And then this allocation ratio is 1. And then, whoops, after you do that, you press the calculate button that you can't see right now, and it gives you all this information. So if you have a sample size of a total of 160 people, broken up into 80 people in each group, you'll get this power of above 80% or 0.80. So you have to have at least 80 people in each of your groups in order to get that effect size and the power you are looking for. There's other ways to do this. This is another one. It shows you with a table. So if you wanted the power to be 90% instead of 80 in that same, with the same effect size and everything else, you can look on this table. You would need a total of 210 people, so 105 in each of your groups, at least. Now remember, if you go out and ask 210 people to be in your study, you're going to have people who say no, And you're also going to have people that say yes, and then at some point drop out. Maybe they die, or maybe they get bored, or maybe they get mad at you, and so they leave. So you have to remember that if you need 210 people to get that power size, you need to collect more than 210 people's information. So here you would want to collect at least 250. At least. So this is the other resources for power analysis. So if you ever want to do this for fun, this is where you can go. This is the one I showed you some screenshots of, and then there's other ones here. Questions? I know, this was